Hello, everybody. My name is Charlie Romine. This is lab number 4 for Physics 2211. Let's get right into it. So, introduction today, and in this lab, we're talking about conservation of energy and sort of energy principles as we've gone through them in class. And then we're going to look to verify the conservation of energy by seeing that the change in energy in our modeled system, at least, is zero. So, important physics ideas as seen. The first four have been pretty consistent through all of our labs. That net force is the sum of the forces. Momentum's not super important for this one, but it is. You could use it for the velocity and position update formulas, which are the same as they always have been. The new ones, the important ones, are the last four, and actually the last one we have used before, but is so K. Capital K or kinetic energy is 1/2 times mass times velocity squared. Potential due to gravity, or that mu g, or not mu, UG is mass times gravity times the height of an object, and you can set that 0 point wherever you want to best kind of fit your problem. And then the potential due to a spring is 0.5 kx squared, where x or s, depending on how you want to denote it, is just, and that should be lowercase x, is just length minus the stretched length minus the relaxed length, which are those L and L naughts. So then, as we move along, we got our initial conditions. The on the paper is how you would solve for your spring constant and relaxed length. That it was actually me using different numbers. So just ignore the numbers and look at the variables because those are all correct. It's the correct math. The way I did it was to set up a system of equations with two separate masses hanging from the same spring, and then to solve for k and the relaxed length from there because you have two unknowns and two equations. That gets us to our initial conditions, which are in this picture of the code. Gravity is always 9.8. I calculated out the K value for the spring to be 6.83 newtons per meter, and then the relaxed length to be 0.123 meters, and then that L at the bottom is the length used. So the length minus the L initial, that's the initial position, which is the ball's initial position minus the spring's initial position. Computational code is pretty simple here. We go through the force gravity, which is just the force times the force of gravity is 9.8 times the mass. And then we've got the force of the spring, the force added together. We've got our position and velocity update formulas here. We've got our things to sort of find L that I walked through a little bit on the last slide. And then our energy, and then this part here is just the energy formulas in code for kinetic energy, gravitational potential, spring potential, and then total energy, which is just all three of those summed together, plus rotational kinetic energy, but we don't worry about that for this lab. And then the deltas, so the delta kinetic, the delta change in potential, gravity, and spring energy is just the new value minus the last value through this loop. So yeah, so we move on. When we run that with the data that I found in Tracker, we get to these three graphs. The first one is our computational model entirely. You can see the three types of energy and how they all sum to zero all the time, which means that energy is indeed conserved, and that principle remains true. And then in the other graphs, there's the y and the x position as they are in the model versus the experiment. And as you can see, they're a little different. This could be due to a lot of things. First, insufficient tracking. Tracker is not perfect. And you have to click yourself usually, or at least that's how I did it, which can lead to a little bit of error. And then also work is done by air resistance in the real world. Air resistance is a factor, and we do not calculate or kind of account for that in the lab. So those two things can lead to this deviation. So for the discussion, as I mentioned earlier, the energy principle is because in the model, the change in energy is always zero. It never deviates. And then for part two, the two oscillations I calculated out to be those two values from the graphs, and then also from that. And then using those, I found the two different K values, which come out differently. And this is because, again, there is work done, and then Tracker is not perfect. So that leads to sort of these two different oscillation values. Also, it can technically oscillate on a different period in the x direction as in the y direction because it can swing back and forth faster than it goes up and down. That is possible.